tonight's special event. I'm John Beacom. I'm the director for the Center for Cosmology and AstroParticle Physics, or CCAPP. And one of the mission of CCAPP is to do three things: to explore the frontiers of science in physics and astronomy, to train students and postdocs on the cutting edge techniques that we use to do this, and most important, to share the exciting results with the public. We're aided in this mission by a generous donation from the Biard family. And this donation is called the R. Jack and Forrest Lynn Biard Foundation Endowment. And what that does is it enables us to run this lecture series. This is the 13th year, and we're delighted to have another exciting speaker tonight. And you can read all about Captain Forrest Biard, on our website, who is the one who endowed this and named it in honor of his parents. He had an extremely interesting life story, and I recommend it to you. But first, I'd like to introduce my colleague, Professor Todd Thompson, who will introduce the speaker.
Hello, everyone. Thank you. I'm Todd Thompson, professor of astronomy and physics and member of CCAPP here at Ohio State. I'm delighted tonight to welcome and introduce my friend, Professor Sera Markoff. Sera is a professor at University of Amsterdam. She's a theoretical astrophysicist working on a wide variety of problems related to how material falls into and is ejected from black holes, how those black holes affect their environments, and how particles and radiation fields are produced in the near environments of black holes. Sera works on everything from the macroscopic effects of black holes on their galaxies to the intricate sort of microscopic level interactions between plasmas and particles. Sera is the author of 200 some papers on these subjects, including some of the most well-known and most high impact work. She's also been a leader on the Event Horizon Telescope collaboration, who produced the first images you see here of the supermassive black hole in M87 and in our own Milky Way. Sera did her undergraduate degree at MIT in 1993. She then did her PhD and master's degree at the University of Arizona in Tucson in theoretical physics in the year 2000. She was then a Humboldt Fellow at the Max Planck Institute for Astronomy in Bonn, Germany, and then an NSF postdoctoral fellow at MIT. She then joined the faculty of the University of Amsterdam in 2006 and was promoted to full professor in 2017. Her awards are numerous, especially as regards the EHT collaboration as a member thereof. Sera shares the Breakthrough Prize in Fundamental Physics, the Bruno Rossi and Berkeley Prizes from the American Astronomical Society, and about 10 others, including the Diamond Achievement Award from the U.S. National Science Foundation and the Smithsonian American Ingenuity Award. Sera is also the member of the Royal Holland Society of Sciences and Humanities, has won a bunch of career awards, and is a fellow of the American Physical Society. I'm going to keep going. I wanted to highlight her work in diversity, equity, and inclusion. Sera's also won awards for making our field more diverse and for helping educate and bring to physics and astronomy underrepresented groups. I first met Sera in 1997. 25 years ago, as I started my PhD at the University of Arizona. She was one of the seasoned and seemingly much older and intrepid senior graduate students who I looked to with some awe and fascination. She was then and now a guide on how to act, how to do science, how to think, and how to, in some cases, fight and resist the establishment. She was then and is now a great role model as a strong and forthright person on an exciting path. It is my pleasure to have her here, to see her again after a long time, and it is my honor to introduce her to you. Let's welcome Professor Sera Markoff.
I got so verklempt with Todd's introduction that I got a little frazzled. Anyway, thanks so much for all of you coming out tonight, spending your Wednesday night in a big box, hearing about black holes. I hope my voice holds up. I've been talking so much in this visit. It's been fantastic. And, I was supposed to come here actually. The original date of this talk was scheduled for April 2020. And the world had other ideas about what was going to happen. So things got, canceled and postponed and rescheduled and so on. So I'm really happy to finally be here to speak to you about this. So the general context of my talk is going to be, sort of obviously these two first really groundbreaking images of two supermassive black holes. That's what you're looking at. And these were taken with the Event Horizon Telescope project, which I'll often say is EHT for short. And basically, before I get into the talk, I just want to say a couple things, kind of a preamble, that when I talk about the work of the collaboration of the EHT, I'm really representing a team of over 300 people, many of whom were young people. So this isn't, my work. And I think that's really important to clarify that. And along the way, I will sometimes show some of the work from my own group. And I've put a list of my students and postdocs, past and present, and some collaborators who I work with. But I always put their names in that color orange at the bottom of the slide. So whenever you see that, you'll know that young people, like many of you out there, actually led a lot of this work. And I think that's really important to point out. Okay, so let me introduce you to these black holes if you're not familiar yet. The first ever image of a supermassive black hole is the one you see on the left. And this is named M87 with an asterisk after it. And this is because M87 is the name of the galaxy that this black hole is in. And then the asterisk we pronounce as star is to let you know that we're talking about the black hole in the center and not the galaxy itself. It's kind of a convention. And this black hole is the new result that just came out a few months ago. This is, I would say, our supermassive black hole. It's the supermassive black hole that sits in the center of our Milky Way galaxy. Now, you would think it would be called Milky Way star by the same conventions, but because astronomy has a lot of old history to it, and the center of the galaxy looks like it's sitting in the Sagittarius constellation from our point of view, it's called Sagittarius A star, but that's too much to say, so we say Sag A star. So you'll be hearing these names throughout the talk, and you can kind of tell which one is which because Sag A star is a little bit more lumpy. Anyway, if you just looked at these pictures, right, I think unless you knew ahead of time, as you've been told, that you're staring down the maw of two enormous supermassive black holes, you probably wouldn't really find this all that impressive, right? I mean, they're like fuzzy donuts, and what does this really tell you? And we know that, Hubble telescope gives us much prettier pictures of galaxies and star formation regions and so on. But what I hope to tell you tonight a bit and give you a feel for is just that I personally think this is just an incredible feat of, human ingenuity and curiosity and persistence to get to the point where we could do something like this. And so that's going to be kind of the sort of theme of this talk. And so the outline is, before I really get into going into what we did and the instrument itself, I'm going to actually spend most of the time talking about this kind of context. So what's the history of thinking about black holes? How do we get to this point? Which is a really interesting kind of I would say, 100-year journey where humans had to reckon and kind of come to terms with the fact that the universe is a lot weirder than anyone would have thought it was even 100 years ago. And then I'll move on to talk more about why do we care? Why are we trying to study black holes? What are we learning from them about what do they do in the universe astrophysically? And then with that context in hand, I think you'll be better prepped, to really get into what it is that we saw and why did we do it. And finally, if I have time, I'll say a bit about what's coming, on the event horizon. Okay, so, I think it's always good to just take a minute and think about human existence. I like to do this a lot. I mean, depending on who you talk to, right? But humans have been conscious and around on this planet for at least some hundreds of thousands of years. And all that time that we've been here, we have been on a planet floating around in a galaxy, well, in a solar system, in a galaxy, in a universe, and we had no idea about it until really less than 100 years ago, around 100 years ago. So we are really living at a privileged time, I think. And I mean, of course, I'm biased. This is my field. I think it's cool. If you talk to a biologist, they would say CRISPR is everything and, curing disease is the big innovation. But to me, this is what I find really exciting. And the fact that, basically, 100 years ago, we sort of thought we hardly knew about fundamental particles and fundamental forces, and somehow this, gentleman, Einstein, and some of his friends started thinking about the fact that actually space and time, which we think of as two very separate things, are actually a linked four-dimensional sort of fabric that we're embedded in. And then weirdly enough, this fabric gets bent by heavy, massive objects or high concentrations of energy. And that bending of space-time forces everything, including light, to move in that direction. But normal stuff as well is forced to move in a direction that we interpret as a force, but it's actually not a force, gravity. So if I drop something, right now, you would think, okay, Earth is pulling this down via the force of gravity, but actually Earth is bending space-time, and it's making that object fall and move in that direction. And, if you stood on a soapbox like Einstein sort of did 100 years ago, people would have thought, that's kind of crazy talk. But it turned out that less than about 4 years later, when he started proposing this idea, it was actually confirmed, which is pretty fast progress for our field. And so a guy named Eddington organized a sort of expedition of gentlemen down to the Caribbean, where they looked at a full solar eclipse. And what they were doing was testing the idea that Einstein was putting forward, that the sun's, big massive thing would bend the light from stars that are way off behind it by its mass. And then by looking at during a solar eclipse, they could see this light very close to the sun's rim. And then when the sun moved out of the way, they could test, if the position changed, and they confirmed this. So within his own lifetime, and very fast, he became a very famous guy, right? I mean, Einstein became very well known, but even before it was confirmed, people started thinking about the consequences of his theory. And don't worry, I'm not going to get into like a long historical thing, but it's interesting. Some of you might have heard the word Schwarzschild radius, which is another name for the event horizon. And it came from the fact that these two guys, Schwarzschild was already a pretty famous person. This is the way science works. Droste was just a grad student in the Netherlands. They actually came up with this idea independently, but we only have heard of one of them. So I just think it's always good to sometimes give a little credit sometimes to the underdog. But they were thinking about the effect of applying Einstein's theory to a spherically symmetric, would say, a round object like a star. And and they realized there was something, as they were doing this, a little bit hinky in the math, that there was this radius, this distance, that somehow if stuff went inside of it, it would never come out again. You'd lose any kind of signal. And this is what we call the event horizon. But at the time they were thinking about this, it was actually inside the radius of a star, of like a normal star. So nobody thought that this was relevant at all. Like it was just a kind of weird curiosity, probably not physically important. However, not that long later, after, I mean, unlikeliness or irrelevancy doesn't often, stop scientists from thinking about stuff, especially if it's a kind of irresistible problem. And this problem of bending of light and gravity was, in space-time bending was very interesting to people. And so already, and this is a diagram actually from 1920 from this guy named Van Laue, but basically they started thinking about what would happen if a star did happen to collapse and form an object that was inside its own event horizon. Then you wouldn't see anything. It'd be something like a dark star. And then they started playing, this is basically early ray tracing for those of you who do video games, they were playing with pen and paper and shooting photons, shooting particles of light at this dark object to see what would happen. And if the photon hits the event horizon, it goes in and you never see anything. But what they found was if you got it at just the right angle, then, sorry, let me get there. If you get it right at the right angle, you sort of skim this black hole and you could go around many, many times before you escape. And so this creates a prediction where if you were looking at this dark object from a distance, you would see a ring of light right outside the event horizon from light that's nearby that gets bent and sort of focused around the black hole. And the fact that the rays are bent is basically exactly what your glasses do or telescopes. It's called gravitational lensing. The bending makes the object look bigger. So the prediction is that you would have a ring of light that's 5 times bigger than the event horizon on the sky. And this is everything you need to know in a way about our image, but they didn't even know these things existed. At the time this was all happening, again, we didn't even know as humans, that there were other galaxies. People were arguing, is there galaxies? Is there a universe? What is going on? So I think it's kind of amazing that this was so prescient, right? And here we go, 100 years later, in 2015, we are able to see tiny ripples in space-time, which are called gravitational waves. And we can see this from merging of things like black holes. We've discovered tons of black holes. I like to call this this is sort of the bat symbol of black holes. I like to call this this is sort of the bat symbol of black holes. It's a kind of infographic. I don't know if you can see the writing here, but this is the mass of the black holes, going from a few up to hundreds of times the mass of our sun. These are black holes that form as the end stages of stars. So this is exactly a collapsed star that forms a black hole, and then they merge and they form bigger black holes. But at the same time, even a few years after that, we actually could see supermassive black holes via a completely different technique. We're able to see the unseeable. And that trajectory is what I mean by, just human ingenuity. It's just an incredible story, I think, that I find really inspiring. So I wanted to share that with you. Now, the thing to remember is that at this time, there was no name for this, or there started to be a name, but it was a pretty unwieldy name. So I want to spend a few minutes before I really go further telling you the story of the name black hole, because I also think it's interesting. So how many of you have heard of John Wheeler, who's the physicist who came up with the term black holes have no hair? Can I see? I mean, the scientists in the front, I know this one, I'm looking more to the back. This guy, he was like the madman of advertising in physics. He was a famous physicist, but he was very catchy. He came up with a lot of catchphrases. This one stuck, and he said, basically, black holes have no hair means that once you have a black hole, it's pretty much its size and its rotation and its charge tell you everything about it. And there's no hair, there's no distinguishing features. So he was really good at marketing, and a lot of people assumed that he came up with the term black hole because he also made it, he sort of marketed it. But it's a really interesting story where it came from. What happened was people used to call these things gravitationally completely collapsed stars. And that was a mouthful, and it was difficult. And so he was giving a talk and he said, I really wish I had a better word for this. And this guy is a British scientist, Robert Dick, screamed out during the talk, what about black hole? And John Wheeler liked it and started using it. And that's how it caught on. And this was at the time when we started realizing black holes were real in around the early 60s. Where did he get the name? It's actually a really interesting story. Turns out that during the period of time when the British Empire was trying to expand into India, more commercial, using like the East India Company had a garrison in Calcutta, and they basically were trying to sort of keep control of, the locals, and they had a little prison that the soldiers called the Black Hole because people would go in and they wouldn't come out. And so naturally, the locals weren't really happy with the British about this. And at some point there was a rebellion. And so the people started to fight back, and they actually took all the British soldiers and packed them into their own prison, about 150 of them, and almost all of them died. So this made it into the newspapers at the time back in England. These pictures were there. It was kind of a real horror and shock to people. And so this term made it into the lexicon. And apparently Robert Dick used to walk around talking about losing his socks and things to the black hole. And then, he applied it to this object, and it's such a good term that I think it resonates. It is exactly what it sounds like. It's this object that nothing comes out of. It's dark. It doesn't emit light, and things get lost in it. So, I think the ultimate proof of this is how much people use the term black hole, right? This is just in our lexicon now. We use it. It means something to us. And I looked online, and you can find all sorts of things like books with the bad Star Wars fonts coming out about marketing. Lots of stuff on the internet about you want things to disappear, get a black hole cat mat. I mean, I find it pretty amazing. Appetite enhancers, the other way around. But I don't think as a group or as a collaboration in the EHT, we were really prepared for the reaction to our results. And, when we saw the memes, the social media, we knew that we'd really kind of hit home with people, that people were trying to kind of own this. And there's other ones that are much less politically correct that I should probably can't put up here. But, I love this. I think that this is the best kind of, outreach, that people really took this on. And I just want to end this little part of the talk by just saying there's a quote that came recently. The Fields Medal is kind of the Nobel Prize for mathematics. And the recent winner, James Maynard, he was actually talking about prime numbers. But I feel like this really kind of applies to black holes. Why are we so fascinated about these? It's this tension between being somehow simple and fundamental, but mysterious and poorly understood. So with that, what I want to do is start to move on and tell you a little bit more about now, what we know about black holes. And what I should say also is that a lot of the history of how we actually discovered black holes, I sort of skipped over, but I do have a couple slides on that at the end if people have questions, and I can tell you a bit more about that history. Is interesting as well. So Many people seem to be anxious about black holes when I talk to them. They worry that we're going to fall into the black hole, or there's a black hole in the center of the galaxy is going to eat us. This is my reassurance slide for you, but I also want to tell you a little bit about what black holes do. They're mostly harmless. Most of the time, black holes sit around doing very little except having strong gravity. And that may sound scary that something has strong gravity, but don't forget gravity is the same no matter who's using it. So, when something is gravitationally captured, then it often goes into orbit. So we are gravitationally captured and bound to our sun. We've been safely circulating said sun for billions of years without falling in. And that's exactly what happens with black holes. So they can capture things, but it's actually not that easy for them to get fed. And they sort of, stuff can be bound and sort of go around. So when a black hole's in its quiescent phase, and this is not our galaxy because we're not able to see our galaxy from this angle, but it's a kind of a twin of ours. If we could sort of fly out of the Milky Way, we would see a galaxy that looks sort of like this, and there's a center, there's a black hole in the center. We think there's a supermassive black hole in the center of pretty much every galaxy. And the reach of this black hole, the ability for it to actually capture things and pull it into orbit is about 100,000 times larger than its own size, or the event horizon. Now that sounds like a pretty big region, but when you compare it to the size of the entire galaxy, oops, why is this jumping ahead? When you compare this to the size of the entire galaxy, it's like Milky Way is about 500,000 times larger than this reach. And on this figure, it would basically be a little tiny dot that you couldn't even see. So from where we're sitting out in the suburbs of our galaxy, you could replace this black hole, Sagittarius star, with a rock, and we wouldn't notice a difference. So when a black hole is in a kind of quiescent dormant state, and the majority of black holes in the universe are in this dormant state, that's pretty much what they do, is they sit there doing very little. However, the story would be kind of boring if that's where it ended, right? But black holes go through cycles of activity, and we don't fully understand what drives this is one of the big questions, but somehow they seem to be able to get more material or get fed, or something happens, and then they become what we call active. And when they become active, something very different and dramatic happens. This is an active supermassive black hole, and I'm going to take you through what we're seeing here. You see 3 different color scales, and that's because black holes and a lot of astrophysical things are emitting light across the electromagnetic spectrum, also in frequencies our eyes cannot see. So from radio all the way up to the gamma rays, and then optical is the little bit that we can see. The white on this figure, the white things, this blob and this blob, these are this is a Hubble image, optical. So it's like what your eye would see if it was as good as Hubble's eyes. And you're looking at, these are not stars, they are each galaxies. Each a galaxy with a black hole inside. They're all bound together in what's called the cluster of galaxies. It's one of the, basically the largest bound structures in the universe. And it's kind of the nursing ground of galaxies. It's where galaxies are born and they grow and they merge together and make bigger galaxies. So if we want to understand all this, how galaxies grow, this is kind of an important place. Now here in the center, you have a supermassive black hole in this galaxy. And in blue, we see radio light. So we've shifted it so you can see it with your eyes. You wouldn't be able to see it. And what's happening is the black hole is ejecting these huge, what we call jets of magnetic material, basically at the speed of light almost, from right outside the event horizon. And the galaxies in here, these jets are billions of times bigger than the black hole, much further than the reach. This is how black holes actually talk outside their reach and can affect the largest scales. And this pink stuff is actually X-ray gas. So basically the gas in this cluster has been heated up to the temperature of the sun. Now space is really cold, and stars like to form in very cold regions. So all this heat and energy that gets dumped, and we can actually calculate how much energy is dumped by these jets by looking at how much gas was pushed out of the way, basically. So we can compare these images and we see these sort of bubbles form. It's about 100 billion supernova of energy can be deposited during one of these active phases. And what this does is it actually stops the galaxies from growing. So what we think is the way the universe looks today, with this distribution of galaxies, maybe our own galaxy, star formation is very influenced by the actions of black holes when they're active. So this is why we want to understand this. But, the problem is, that all of this is happening very close to the event horizon, and we haven't had access to this region up until now. So now I'm starting to get into a little bit about, what these images are telling us. So we've got these two black holes. Remember, the blobby one is Sagittarius Star, you can always tell, and M87. And, the images look pretty similar. And what that's telling us is that we're focusing in on the region right near the event horizon where we have this light bending effect that I just talked about that was predicted, back in 1920 or something. But if we look at their scenarios where they live, they're in completely different environments. M87 is a huge elliptical galaxy. It's black hole. It's about 6.5 billion times the mass of our sun. This black hole is basically as big as our solar system. It's one of the biggest black holes that we know. And that's one of the reasons why we can see it. And it's also launching one of these big jets. So we're catching it in its active phase. It's, basically interacting with and affecting its galaxy. Now, Sagittarius A star, again, this is a proxy, it's not really our Milky Way, is a little black hole, all things considered. It's 4 million times the mass of our sun. It's in this dormant state. You can see that the power being emitted right now by M87 is like 1 billion suns compared to the total power in our little kind of mediocre black hole in our galaxy is only 1,000 suns or so. And so what we want to start doing is understanding, what is this region telling us? What can we learn about how this whole process is initiated? What drives this? Why does one look like one and the other? And we think over time they will swap, and that we know in the past Sagittarius Star probably used to have a big jet, and maybe it has one now, but we're having trouble finding it. Whereas M87 in the past maybe didn't have one. So this interplay is a very important part of what we're trying to understand. And we think that big galaxies like this grew by little galaxies merging, and then their black holes will find each other and merge as well. And so the way that this process is also regulated is partly by what we call this feedback, by these things, jets and outflows that influence this. So this is kind of the bigger context of how we're interested, these grand cosmic scales of all these huge black holes merging, growing, changing, and affecting their galaxies. And this is a beautiful image from Webb. You might have seen it. This is 5 galaxies in the process of merging. We see this all the time. And we're trying to understand, this one has an activated black hole, for instance, and then we can look at it in different wavelengths and try to understand what's going on. But we only have 2 black holes right now in the universe that we can make a direct image of. And that's why the Event Horizon Telescope is so important. It gives us access to information that we wouldn't have for any other black hole in the universe. And we try to learn things, and we can try to extend our knowledge to all the other ones. So, at the end of the day, what we're really trying to figure out is how to predict what's going to come out of these regions near a black hole as a function of what goes in. That's a simple way of saying it, but it's something that we're really missing more from the theoretical side at the moment. Okay. So now I think you guys are all primed a bit. You understand more about, the history and the context and why we're interested in this. I'm going to tell you now about the project a little bit and about our results and kind of what it means. And then we'll see how time goes to get to, where we get to the last part here. So here I go with my collaboration hat on. Now, we are a group of over 300 people spread across the globe in about 80 different institutes, many different countries across 19 time zones. Now, that was great before the pandemic because we would just fly all over the world, talk to each other. The latest black hole image, which happened since the pandemic from Sagittarius Star, we had to do all of that work remotely. And for those of you who, maybe understand this, we were having telecons at 2, 3 in the morning. We had to shift the pain to the collaboration. So it was really a lot of work by a lot of people and very intense. We finally got to meet in person again just this past summer. So things are starting to come back a little bit more to normal. Now, the Event Horizon Telescope is not an Earth-sized telescope, which is what this would look like. If we had the money, I think we would probably build it, right? But the idea is kind of a trick, which is to come up with a way of building an Earth-size like telescope. And the reason is that the bigger your telescope is, the better you can see. And these black holes that we're trying to see, even though they're the 2 best candidates for us because they're the closest and the biggest, to give you an idea of the size on the sky, you hear people say things like, it would be like looking for an apple on the moon. Or if you were sitting in New York, trying to read a newspaper in Amsterdam, where I live. So that's how good your telescope has to be to give you some idea of the precision, which, again, sounds kind of crazy, right? So we need an Earth-sized telescope. And a real sort of regular optical telescope, you have a mirror, and then light comes in, and it gets collected in the sort of central area, and then you add it up and you have your image. Now, radio telescopes work somewhat differently. I won't go into a lot of detail about that. But we do something else instead, which is we put telescopes. Well, we didn't put them there. I'm going to say something about this. We use telescopes that are already built and we borrow them that are across the Earth, and we combine their signals using supercomputers. Now, of course, in the ideal world, we'd cover the Earth in these little radio telescopes, and we have almost the equivalent of an Earth-sized telescope. But again, we don't have that much money. We don't have that many facilities. So the fact that there's a lot of gaps in this array means that we have imperfect vision. And that's partly why we see such a fuzzy ring. So what's really important is that we use the turning of the Earth together with this array to try to add up the light. And each distance between the different telescopes kind of gives you a different size. You know, the distance between the telescopes corresponds to a size in the system that you're looking at. So if you were the black hole looking at Earth, which is sort of what was happening, the Earth is turning from your point of view, and these baselines, which are the lines between two telescopes, tell you about what, you know, the longest baselines probe the smallest scales, let you see the smallest scales in the black hole, and the shortest baselines give you sort of the larger scales. So the smallest and largest distance between these telescopes kind of define what we can see. We can see around, you know, a bit outside the event horizon and up the event horizon, and then we can see out to a little bit further because of this. Now, what's really important to remember is that one of the key assumptions is that we're assuming that the black hole's not changing while the Earth is turning, because we're trying to add everything up. So it takes about 24 hours, you know, for the Earth to turn. And then we think, you know, and that turns out to be correct for M87 star. M87 star is a huge black hole. It's hardly changing at all. And so we could do this. But for Sagittarius A star, it's a small black hole and it's flickering and it's doing all sorts of interesting stuff. And so that was the reason we did M87 first. People thought, you know, why wouldn't you do our own galaxy's black hole first when we observed at the same time? And I'll say a little bit more about that. So this is, I'm going to take you through this, but this is just to give you an idea of how our data looks. So you're seeing the same movie here. This is a sort of kind of like a plane that gets filled out. And what you can think about is just the more squiggles you see on this plane, the better our telescope is. If we had a perfect Earth-sized telescope, this entire thing would be full of color. But what you'll see is that as these baselines move with the Earth, it starts to fill in little bits on this figure. This is our raw data building up. And then these are showing you 3 different methods of reconstructing the image from our raw data. Now, don't worry too much about you know, the details of this, but I think it's just to give you a feeling that it's very sparsely populated, and it takes the Earth turning to start to build up the data that we can start to reconstruct the kind of image that we're looking at. And one of the things that we do is we had different teams that worked completely in isolation from each other, because in science, you don't want to have people influencing each other and talking if you especially know what you want to find. And so one of the big verifications was basically that the teams all unveiled their results to each other, having not talked at all. And this is the kind of thing that we saw where one was a little bit fuzzier. They used different methods to reconstruct the data. One was, you know, some are more ringy. And this is because we have such, you know, a sparsely populated Earth-sized telescope that we have basically a very fuzzy image. And we don't know which one of these is really right. That's our uncertainty. So we added them all up and averaged them. And that's how we made the final image, basically. That's the best that we can do. And the only way we can do better is to put more telescopes on the Earth or go off the Earth into space. So, you know, one of the things I'll say is that we've been starting to put some more telescopes into the array. So this is the array as it looked in 2017. We did not have the Greenland telescope then, and these are the results that we've published so far. We're just starting to work on 2018 and beyond. So we have, and you have to realize we don't own these telescopes. So we have to write competitive proposals to actually get the time on these telescopes. So it's a really hairy business. Every year we're having to write these proposals almost at the same time that we're doing the observing. We have 8 facilities in 2017, and then in 2018 we added 2 more. And we had the Greenland telescope, and we had 1 more. We added a Greenland telescope, and then we lost 2019 to technical problems. In 2020 was the pandemic, so everything was shut down. And so we then only started observing again 2021, 22. We added a couple more facilities. Each campaign, we borrow these facilities for about 2 weeks, and then we're given, not the whole time, but we're given like 6 or 7 nights, and we have to do a whole rigmarole of trying to decide which night's the best night to observe what. And it's this whole detailed process that we have started calling, trademark Vincent Fish, who is one of the schedulers, the Sudoku of scheduling. And to give you some idea, it started with tables like this, where basically we have the dates of the observation. We try to align our observations with other telescopes, both in ground and space, because as I showed a bit, black holes are emitting light from across the electromagnetic spectrum, whereas the Event Horizon Telescope only looks at one frequency. So we're trying to kind of get complementary information at the same time. And we have this whole table where we try to like guess all the scheduling and decide, which one's best. And by now we've gotten so much better that we use Excel sheets. So we now have detailed Excel sheets where we, make color coding for how much coverage we have on the ground for each night. And we have color coding for the weather. And you can see like on this day, this was from this last year's campaign, orange and red is bad. So this shows whether we observed or not and which source we looked at. And here we didn't observe, so you can kind of get an idea. And every night, 2 hours before observing, people are all over the globe at the telescopes. We're at what we call like command central, mostly in Zoom in our pajamas, discussing, whether or not we should trigger the observation. It's very stressful. And here's a little picture of people at the observations. During the pandemic, we actually got to run a bit more remotely. And I think that's going to be the trend, but we always generally need somebody there because weird things happen. Telescopes, get snow on the receiver and you need to go up there and kick it sometimes. And then it's good to have people. And then this is, what happens is the data are recorded locally and it's a huge amount of data because what you have to do is you have to tag each wavefront of the light with an atomic clock and record it. It's like petabytes of data. So you cannot send this over the internet. You have to fly it on a plane, which has to go to a supercomputer where it's basically what's called correlated. And you're looking for a signal between sort of a matching signal between all of these different wavefronts that come in using the time tagging to finally find the one where this is basically means you've got a result. And then you can finally reconstruct your image. So I hope that this gives you a little bit of a sense of, what's involved in the observations. And now I'm going to talk a bit about, what does it all mean? What have we actually learned from this? So this is to give you a sense of how we do the interpretation. Making a picture doesn't tell us that much in a sense. I mean, the size tells us about this test of the ring and general relativity, which is, Einstein's theory. But there's a lot more we want to understand, like this connection to these launching of these big jets and how does this all work? So we use supercomputers and we basically build black holes in a box. We put the space-time warping in there. We wrap, this is basically a donut of material that's wrapped around the black hole. So you're looking at a slice of it right now. And then we seed it, this black lines are magnetic fields. So it's, what happens is, I'll just show you, this is work. Here you start to see the orange names of students that ran this and even wrote the code. Basically the black holes here, and this is size scale in event horizons, basically. And you launch these big jets. This is sort of the state of the art at the moment, that we're able to do very high resolution and study all this physics near the black hole, but also go out to the largest scales. And we try to compare this to also the observations that we have of these big jets and put the whole picture together. But we need to be able to make images based on what's happening down here. So this is like what I would call volume rendering. So this is just showing you kind of the systems. You have this disk and you have the jet. The thing is that we lose all the information about the large system with the Event Horizon Telescope. Because remember I was saying that what it can see is basically set by the size of the planet. And we're trying to see the event horizon, which means that we're kind of missing all the other information. And I'll show you an actual simulation of how this works. This is sort of that disk of material, and here are the jets again. And this is also at a what it would look like if you looked at it with a perfect telescope at a different frequency, at sort of lower frequencies. And as we ratchet up the frequencies of the event horizon telescope frequency, we strip away all this information and we're only able to see this part of the system. So we make an image of what's happening just outside the event horizon, and we make movies from these simulations, but we don't really have this connection yet. We have predictions for this connection to these large jets, but we haven't put this all together in these early works. And so that's a little bit moving towards more the future, is trying to build back this information about the large scales. So if we think about what we're seeing, if we had perfect planet-sized telescope, then what we would see is basically a bunch of stuff moving around the black hole. And then this feature here is that tight ring called the photon ring, which was predicted back in 1920 of the photons being bent around the black hole. And that basically gives you the information about, is general relativity correct or not? Because that's a direct prediction of what general relativity, says. You're going to have this size scale in the sky that's basically 5 times bigger than the event horizon. So if you come in knowing how massive the black hole is and how far away it is, you can predict how big on the sky it should be. And that was our test of general relativity. Now, this is what EHT sees. So if you simulate, the blurriness, the problem is we're trying to pick apart the general relativity light bending from all this kind of fluff that's on the outside that's changing, which is from, all this stuff moving around outside the black hole. And that's a very difficult process. And so that's one of the reasons we also have a sort of uncertainty on how well we can at the moment test the theory of general relativity. But at the moment, it's looking pretty good. Okay. So what we do is we make simulations. So we, at the time for M87 star, for the first papers, we made 43 of these supercomputer simulations. And basically this is, these are all like hundreds of thousands of CPU hours, and we have lots of data, and we make thousands and thousands, so about 60,000 snapshots of all these different black holes, of different types of black holes. And we're trying to figure out which one's the right one, right? Which one matches our data. And so we compare everything. It's a big thing. And if you're really curious about the details, you can read the paper. But what we learned was, more or less by doing this, that the size of the shadow is definitely consistent with the predictions of general relativity. The shadow seems to be quite circular. And what that tells us is that we're kind of looking down on the black hole or looking up at the black hole. It would be a bit more squashed or distorted if we were looking at it sideways. And that actually lines up with what we know about these jets from M87 star. These huge jets coming out kind of tell us that orientation as well. So this black hole, it's spinning, and it's sort of, the jets are kind of coming out towards us. The asymmetry, the fact that this is brighter here, tells us this is what's called Doppler boosting, Doppler shifting. It's the same thing that happens when you hear a train going by. And as the train comes towards you, it gets sort of, higher frequency and louder. And then as it goes away, it tails off. Light does the same thing. Light moving towards you gets brighter. So we know that the stuff is kind of moving in a kind of clockwise direction on the sky. And then I didn't talk much about polarization, but we basically understand that there's very strong magnetic fields, and that helps us understand how these big jets are pushed out of the black hole at nearly the speed of light. But we really can't yet connect this image to the larger scale jets. And so we didn't get as far as we would have liked. I think in a lot of ways with M87, it was really a proof of concept that we were able to see a first picture of black hole, see the depression where the event horizon is, have everything line up the way it should. And the question now is, what else can we do? So moving on to the Milky Way. This is a really cool little movie to kind of orient you. This black hole, our black hole, is so different because we're able to actually see so much more about it. It's right in our backyard, and we knew much more about it going in, which helped us do the modeling, and we can get a lot further. And so this is the plane of the galaxy, and this is an image of what that looks like in the radio frequency. So in the frequencies your eyes can't see, but with very similar to what we do with EHT. And now we're going to zoom in, and we're going to change frequency. So right now, this is what you'd see with your eyes with optical. And as we move closer in, you'll see that we start to see all these stars, and there's dust. This stuff is dust. But we have incredible telescopes now where we can start to see individual stars right outside the black hole. And that's how we were able to weigh this black hole and know exactly where it was and how big it was. Now, this is switching to the X-ray view. So you can't see this again with your eyes. We use these kind of fake colors, but this is what you see in the center of the galaxy, and then zooming in. It's sort of the scales of 10. This is a bunch of stuff around the black hole, but we finally managed to actually see the black hole also in the X-rays, and it's flickering. I'm going to say something about that in a second. And then here are the individual stars now switching to the near infrared seen from the ground. And these are stars moving around the black hole over time. And you might have heard about the Nobel Prize given to this some years ago. Andrea Ghez and Reinhard Genzel were 2 separate teams, UCLA and Germany at the Max Planck, who were looking and mapping these individual stars. And then by looking at their orbits, it's just like what we use to find exoplanets. We can weigh things by doing just the gravity. It's a very simple math actually to figure out what mass has to be inside. And finally, we go down and down and down, and we get to the clumpy black hole Sagittarius A star. But the fact that we knew so much going in really helped us, as I said. And, here we are now, and we have these two black holes. This white ring shows you the prediction of Einstein's theory. And then, the fact that it's fuzzy, now you understand why it's fuzzy because of the limitations of our instrument and our uncertainties and having this non-fully filled out planetary telescope. But still, it's pretty spot on, but we do have some uncertainty. And we have a very small black hole and a very big black hole. And why is that important? This difference in size and mass, 1600, actually means that the time scale on which it changes are very different. So I kind of like to use the analog of fruit flies versus humans. If humans live their lives in let's say if we're lucky 100 years, and fruit flies will live their lives in 24 hours. So little things tend to live their lives faster, and animals are the same way. So for stuff to move around the black hole, for Sagittarius star, it takes something like minutes. Whereas for stuff to move around M87 takes, weeks to a month, which is why when the planet is turning and we're observing Sagittarius A star, it's much more complicated for us to do the analysis. And so that also created a lot of problems for us. Sagittarius A star is flickering. This black hole, this is X-ray telescopes so this is totally different frequencies now. We have satellites in space that look at this. And also from the ground, this is the same facility that looks at the stars around Sagittarius star. And you see it sort of, wait for it, pop. That's Sagittarius star, and it pops in the X-ray, and they pop together often and about once a day. And so it's something like, we're looking at something like the solar surface. This is a picture of the sun, and we're starting to make models that look very similar to this. And we think that this flickering is very similar to the gas in the sun, and we're trying to understand it better. So I won't go into a lot of detail about that, just to give you a feeling about what we're learning from this fast flickering black hole. And of course, we have all of these different simulations. In the meantime, we had more years to work on this. And so we have hundreds of simulations, but what you can see is that the size of the Event Horizon Telescope, the shape didn't rule out very many models, but the shape started to rule out many models. All this data from all these different frequencies ruled out almost everything except for 2 models out of our whole suite. And that allowed us to make much more interesting statements about this black hole. And so where are we now? Well, the best bet models want to have positive spin. For physicists, whether the black hole is spinning or not is part of this non-hair thing that John Wheeler was talking about. It's very important for us to understand the spin of the black hole, because this also helps understand the power of the jets. What's really weird is that they seem to be incredibly similar, but they look very different on these large scales. So we don't understand this. Right now, it seems like all signs point to go for Sagittarius A star to have a jet like M87, but it doesn't. And it's in this dormant state. So this is a real mystery for us that we're trying to figure out in the coming years. And we're trying to understand these flares. So I have just a few minutes left. I'm just going to rush through a couple of things and just say, the same time, remember I was saying we did this whole Sudoku where we organized all these campaigns from ground and space. We haven't yet even really combined all this data. And this is the data that we have. So at the moment we took the picture of M87, we looked at it with all these different telescopes. These are radio telescopes. And so this kind of shows you, like that movie I showed you, where you strip down to the black hole and come up back out to these large jets. We have all that information. This is in the radio. We have X-ray information. This is the Hubble telescope. So we have the optical, we have gamma rays, we have X-rays here as well. And we need to start to connect what we're learning about what's happening near the black hole to these larger scales and to all these different frequencies. And so that's really where the field is going. We're looking at many other black holes. We only can see the event horizon for 2 of them, but we can see very close to the bottom of these jets for a couple of them. And for instance, we published last year another black hole that's nearby. This is M87's jet. So this is not seen by the Event Horizon Telescope, but it's to compare that with this black hole, we cannot see the black hole that we see for M87, but we see similar features in these jets on very small scales, and we're trying to kind of put this all together. And I'll just rush through these and say, there's plans to expand it, because obviously the way to make our telescope better is to put more stations on the ground. And so we have plans to start to, especially Africa, is a really important place. There was nothing here, and so we lost a lot of viewing. And if we can get a station, specifically in Namibia, that would be a really great place. So there's quite a lot of planning going on to expand the array. And I'm going to skip over this and just say, we're trying to connect to the larger scales. But there are so many black holes out there. and we know of millions of them, in fact, even billions from other facilities. And so the next stages are going to be trying to take what we're learning to understand, the largest scales, how the black holes all over the universe are affecting things. And keep in mind that black holes actually affect us. We wouldn't be here. Our galaxy wouldn't look the way it does if it wasn't for the action of black holes, also small ones. And I'm going to leave you with one final thought, because I know John's like telling me to stop, but this is pretty cool. Did you know that your GPS navigation is calibrated using black holes? And this is something a lot of people don't know, but black holes, these bright black holes all over the sky, are very stable on the sky, and they define what's called the International Celestial Reference Frame. These are all black holes that are used by facilities on the ground, very similar to what we do with EHT. These are radio dishes across the Earth, and they look at these black holes and they reference the position. This is how they know their position on Earth. They communicate this to satellites. And so quasars or black holes are basically telling us where these stations are on Earth, which then informs all the telescopes. So every time you use Google Maps, you know where you are on the planet because of black holes. And I think that's a really important thing to note. And we also can study plate tectonics this way. So there's a lot of interesting things to keep in mind. And I'm going to end with that and just say, thanks for your attention. I hope that the level was okay, and ask me questions. And that's it. Thanks.
All right, thank you very much. That's wonderful. We'd like to take questions from anyone who has them. And we have a microphone here, which I think I'm gonna try to.
I think there's one there too, right? Yeah.
There is one there too, but I saw a hand over
Okay.
here. Here you go.
So you said that the Sakai star black hole has an intrinsic time scale of something like a few minutes, half an hour or so, and that you observe it over the span of a night and you average over your measurements. Why is the picture lumpy?
So that's a great question. And it has to do with the fact that when you have an imperfect array, with, basically the fact that we have this sparse array, it can introduce, this averaging can kind of introduce patterns into the image. I actually have an extra slide on this because I kind of thought that somebody might ask something about this, and it kind of is a really nice demonstration of what happens. So this was made by a colleague of mine, but imagine that you were looking at the Dolomites or some kind of mountains, and you're looking at this over time, and basically clouds are coming, clouds are going, and I should have shortened it because it goes for a little while, but it's kind of on the same time scale as the Earth. You can imagine that these things are changing. And then at some point you want to figure out what are you seeing? If you were trying to train a computer to know, what you were looking at, you can categorize these into snapshots, because that's basically what we do, is we can only add up the data up to a certain amount. So we can divide it up and do some kind of clustering where we can say, okay, sometimes our image looks like this. Sometimes our image looks like, something else. And it kind of keeps going until the point that you end up with different classes of images. And what we did was, sorry, it's coming. So our final image, you can see that we have these different groupings of images. This is our average image. Sometimes we see different structures, but we always see these three bright spots, right? And that is probably an artifact of the fact that our telescope is a sparse array. It's not real. In M87, we believe, for instance, that bright ridge at the bottom, because it's very robust, and we've actually starting to see it shift in time. But the little brightness bumps within it are an artifact. You saw that in some of the reconstructions and some not. So we're not too excited about those bumps yet. I think if they held up and they started to change their positions, it might mean something, but probably this is more like something to do with this clustering that we have to do. It's a great question.
Great, thank you very much. We had a question here.
Yes, thank you. And let me preface this question by, I'm not a scientist, the lay public. You mentioned that in order to get better imaging, you need more telescopes on the ground, more time on them, but you also referenced we could also go into space. And I'm curious how the James Webb Telescope may help And are there any other telescopes under development that we are going to put in space 5 or 10 years from now, and how would they be designed to look at this?
Yeah, so James Webb, one of the things is, of course, to hook up all these telescopes, they have to operate on the same frequency of light. And Webb is, basically in the infrared, it's a different frequency of light. So we can't join it together with the Event Horizon telescope because we're looking in the radio bands, which is a completely different frequency, and they have to be the same. But we can look at the same time as part of these campaigns. And in fact, in the first cycle of Webb is this year, it's happening right now, the first observations, we put in a competitive proposal and we got time on the Webb telescope. So it's going to be looking at Sagittarius Star this spring in 2023 in our next campaign at the same time. And that flickering that I was talking about is really important for us to, help understand the black hole. But it's a different technique. It's not this interferometry technique so it's kind of like we can't, put them together the same way. We can't string them together. So what we would need to do is actually take telescopes that are operating in this frequency, which is about 230 gigahertz, if that means anything to you, but it's a specific band and we have to put them into space, and then we have to be able to link them either to the ground stations, which is a very big technological challenge because the data rates remember I was saying that every time we look, we're basically recording almost a petabyte or half a petabyte of data. Currently, there's no way to really get that down, to the ground. So, the people who are thinking about this in the real satellite technology, it's very interesting. They're starting to use these sci-fi terms like tight beam and like laser comm. It's really cool. But maybe that's going to be the solution. Otherwise, we'd have to build the array in space, and then the communication can maybe start to happen up there. The problem is, if you want to launch something into space, you're talking about at least a $500 billion, per dish. So much as we would love to put a bunch of stuff into space and like increase, then of course we get much larger baselines and we'd be able to see other black hole rings. That's the only way we can do it, is to go off planet. Well, talk to your Congress people.
Great, thank you, John.
So like, you know how black holes have a really strong gravitational force? What do they do with the objects that they like pull in? Like, do they somehow send it back out?
Nothing comes out of a black hole. And so what that means is that, if you were unfortunate enough to get close to a black hole and you fell in, you would help grow the mass of the black hole by exactly your mass, but you would be lost to us. And so we obviously have no plans to send people into black holes, not only because they're really far away, but also because, we wouldn't be able to get the information out. But there's a lot of interesting, you're onto something, because physicists argue about whether is the information lost when something goes into a black hole. So like if I throw you in a black hole or I throw a chair in the black hole, will I later be able to tell the difference, and other than the mass? And that's a very deep question. So, but I think the best advice is stay away from black holes, at least that close. If you stay in orbit, you're fine, but don't go in on a straight trajectory.
No, I can't remember the name of the telescope, but it's featured in the Goldeneye movie. The collapse of his radio telescope.
Sorry, I'm having trouble hearing you.
It was in Central or South America, and it was the.
Oh, Arecibo in Puerto Rico.
Did that badly hurt the?
No, because
collection of data?
again, Arecibo, it really hurt astronomy. It was a terrible thing to happen, but it was a different frequency again. So, the problem is this fine tuning of being able to line up these telescopes. We have to be operating at a very narrow bandwidth at the same frequency. So this is what's called submillimeter, which is a kind of a high frequency radio, and Arecibo operates at a lower frequency. So we would love to have had a dish that big, believe me, but it was the wrong frequency. And so it could be retrofitted. People are talking about building, replacement, and we could, if we could get the right receiver on that, would be great.
John, I got one here.
So in 2015, we heard the results from the LIGA experiment where we were hearing about the the collapse of black holes in the order of 10, 20, maybe 50 solar masses. And we're now studying black holes with millions of solar masses. How do we get from understanding how those objects that we can study are combining, are collapsing on each other? How do we get to understanding how these objects grew to these sizes?
Yeah, so this is actually, I would say, we don't know right now. This is a big debate in the field of how you get to these very, very big supermassive black holes. We sort of understand that once you have reasonably bigger sized black holes, that they can merge and grow. But what's happened with instruments like Hubble, and eventually Webb's going to be showing this as well, is we're starting to find black holes that are enormously big very early in the universe. And this kind of challenges the models. So people used to think that the first stars early in the universe might have been bigger, and then these stars would have formed bigger black holes. And that's kind of what we're able to start seeing with these with the gravitational waves. We're seeing these stellar remnant black holes and how they merge and form, but they seem to sort of peak out at a couple hundred solar masses. And we need something that would either be able to grow extremely fast or somehow get bigger than that. So the answer is we are not sure. There are theories that involve dark matter in the early universe and or different kinds of collapse. But it's one of the big mysteries at the moment. And I think it's a very fluid field because we're starting to get new data all the time. But there's this gap, as you saw, between the little black holes and the supermassive black holes. Somewhere in there, there should be what's called an intermediate mass black hole that would tell us something about this evolution. We have candidates, but there's been no winner yet that people are convinced of. So, yeah.
I don't know if this has been covered, but do black holes have a lifespan? And if they do, are you able to measure it?
So this is interesting. So you've probably heard of Stephen Hawking. He's a pretty famous scientist. He was in a wheelchair. There was a movie about him and so on. One of the things that he really got famous for was predicting that you might have a way of shrinking black holes. I mean, we know how they grow. Let's put it that way, that black holes grow by capturing stuff. And if they capture it, it just adds to their mass. But the only way that we know how they shrink is via this process called Hawking radiation, which is a very tiny trickle. It's actually an unobservable trickle. And so as far as we know, black holes will probably pretty much outlast all of us, to very long time into the future. But we've never been able to measure, an astrophysical black hole shrinking or disappearing. Now, there's ideas that, you might form little tiny black holes, for instance, like in particle experiments or so on, but we haven't been able to observe this. So it's a great question, but we just don't, we don't have a way of knowing that. So I would say from our point of view, black holes are probably one of the most stable, longest living things in the universe. And when the universe gets old and cold, as we say, it'll be like the cockroaches. They'll be the last things left. So.
All right, there's a question over here.
Is it possible for one black hole to orbit another black hole?
Sorry, I'm trying to, oh, there you are. Okay. I was like, yes, in fact, definitely. And those, the little black holes that we're seeing from gravitational waves are basically two black holes orbiting each other, and then they collide and form and make a bigger black hole. So it's a whole process of life cycles we're seeing is basically most stars actually form together with another star. So I like to say, stars are kind of like people. They like to be in pairs. But so most of the stars in the universe live in a pair and they orbit each other. And then if a star is big enough, it will eventually go supernova and form a black hole. And then there'll be a period of time where it's eating its other companion, but then eventually that one will go supernova. And if that's heavy enough, then you'll get another black hole. And so you end up with a binary of two black holes. But we also think that when two galaxies merge, their black holes will orbit each other and merge. And there's starting to be some evidence for these huge black holes orbiting each other. So there are space telescopes being built. There's one called LISA, which is supposed to come in about 10 years. And it's going to be studying these supermassive black holes and maybe a big one and a small one orbiting each other.
All right, I think I would like to thank everybody for all of their questions and their attention. There's a reception where you can ask Sarah some more questions. Thank you very much, and let's thank Sarah again.
Thank you.